are in listen-only mode.
All right, I'm going to begin momentarily here. If you can just, if one or two of you could just shout out that you could hear me perfectly fine, if you don't mind, and then we'll start this presentation here shortly. Thank you. All right, I think they said the volume was low. If you could just let me know if the volume is a little louder now, and then I will get moving here shortly. All right, I'm going to give it one more moment here, and I'm going to start here in a second. Okay. Okay, I'm going to start today's webinar here. I want to introduce myself. I am Mike Smid with TEC. I'm the Vice President of Commercial Products for Temperature Equipment Corporation out of Chicago, Milwaukee, South Bend area. The topic we're going to be covering today is going to be chilled water optimization. So we're going to go through that in detail. If you have any questions, what I'm going to probably do is I'm going to answer the questions at the end of the presentation. So I'm going to get going, and then I'm going to answer the questions at the end of the presentation. And if anybody has any questions, they could either email the email that was sent out to you, or you could contact me directly at mike.smid, S-M-I-D, at tecmongo.com, and I could talk to you that way. So what we're going to do here is we're going to look at utilizing a Carrier water-cooled machine and exceeding the ASHRAE minimums by greater than 50% is what we're going to be looking at here. The main core to the product and the main reason why we can get to these 50% levels is going to basically related to the 23XRV variable speed tri-rotor screw chiller 2008 Green Building Product of the Year from 250 to 550 tons. And we're going to go into detail a little bit about this, but mainly what we're going to talk about is chill water plants and optimizing them today. So first step, what we're going to do is we're going to look at the weather. So I'm going to go over the weather, the determinants of chiller energy consumption. I'll briefly talk about the variable speed screw chiller. We'll talk about chill water plant design, and then we'll start going into some actual results that we're going to discuss today. If you look here at Chicago weather, and this is very similar for both Chicago and Milwaukee, if you have a building that operates 24/7, 73.8% of the hours can operate with less than 70 degree entering condenser water temperature. And reason why that is, we're going to go into this major piece on why this is good. And it is, when we talk about chiller efficiency, it's all going to be related to what we call lift. And you're going to hear me talk a lot about lift throughout the presentation. If you look at a building in Chicago that operates 12 hours a day, 5 days a week, still 73.3% of the hours have less than 70 degree entering, have the capability of delivering less than 70 degree entering condenser water temperature. Look in, for instance, our factory which produces these is in Charlotte, North Carolina. Even there, 68% of the hours can deliver less than 70.4 degree entering condenser water, and 58 less than 12.5. So just kind of showing you some background of some weather data and what are the determinants of energy efficiency itself. One of the main pieces on how we're going to get efficiency is driven by this object, which is called a cooling tower, which is something that we don't sell. But when we look at how we recognize efficiency on a chiller, actually any centrifugal with a variable speed drive, basically what that variable speed drive does on a centrifugal machine is it tracks the weather. So therefore it tracks the wet bulb temperature in the tower, and that's the way it gets, that's the way basically you get your efficiency benefits. Okay, it's a centrifugal with a VFD is a part lift device. It's not a part load device, it's a part lift device. So VFDs track the weather. That's one of the key pieces we want to know. When we start talking about chiller energy consumption itself, we're looking at basically we have the mass flow, which is the refrigerant flow, times the lift. Okay, and the lift is very important when we're determining chiller efficiency in a standard chiller plant. Oh, that was a little, hold on. So what we have here is the key piece on trying to figure out how efficient a machine is and what it's, and basically from the efficiency standpoint is we're looking at lift, and it's based on leaving water temperatures. Okay, it's not, I said entering before, but it's really determined on the leaving water temperature. So for instance here, on the cooler, we basically have a 2-degree approach of figuring a 2-degree water to refrigerant side approach. That 2-degree approach, if I have 44 degree leaving water, which means I would have a 42-degree saturated suction temperature. On the condenser side, I would have to be warmer. Okay, so therefore I would be 95 plus a 2-degree approach. I would be a 97-degree saturated condensing temperature. The saturated suction and saturated condensing temperature is a determinant of the chiller efficiency itself. So in this case, we have 55 degrees of lift, but this is based on design temperatures, right? This is that 1% of a year, if it ever happens on a chiller plant, where my building is fully occupied, it's a design day outside, and I'm producing these type of situations. Most of the time, however, this is a design day. This pressure enthalpy chart shows a design day. However, most cases we're going to be able to deliver or have at least 70-degree entering condenser water temperatures. If we're able to get 70-degree entering condenser water, I'm going to assume approximately around 80-degree leaving water, 2-degree approach, so I would have 82-degree saturated condensing temperature. Because I'm able to deliver colder water through the tower, I'm now actually reducing the lift on the chiller. Okay, that's a key piece. So I want a chiller that can do a couple things, right? I want it to be able to handle cold condenser water for consistent hours at a time. All right, I don't want to have it test for cold water. I want it to be able to run consistently with cold condenser water, and that is a key piece of energy savings on a chiller plant. Again, lower lift, less work, lower kW. Okay. Let's look at a single chiller plant. And what we're going to do is we're going to analyze both a constant speed machine and look at a variable speed machine itself. So at the 100% load point, the 2 points are virtually the same, right? So the kW per ton with a variable speed drive versus a non-variable speed drive are going to be virtually the same. Sometimes the variable speed drive may be less efficient. Sometimes it may be more efficient based on where it's at on the compressor map on the machine itself. So when we look at this, as this building load drops, which is the lower axis, as the building load drops, my condenser water temperature gets colder. So as I get colder condenser water temperatures, my machine gets more efficient. So when I'm at approximately around 50% load on the building, 50% load outside, I'm running it at pretty good kW per tons with cold condenser water. Whereas a mechanical unloading device, you are going to get some energy savings at cold water. However, it's not going to be as significant because I'm not reducing the RPM of the VFD motor. So let's look at a 2-chiller plant operation. Okay, so with this, again, I have building load on the bottom, and I have percent chiller load on the side axis. Okay, and down at the 14% load point means I have a minimum of 55-degree entering condenser water, and my design day would mean I have a minimum of around 85-degree entering condenser water temperature. So as I load up a typical building, I'm going to take that building and I'm going to load it up to 100%. After I reach my 100% point, I'm then going to turn on 2 chillers, and 2 chillers will then ramp up from 50% to 100% point. So that's a typical operation of a 2-chiller plant here in the Chicago and Milwaukee area. Now let's look at those 2 pieces. Now before I said on the previous slide back here, I said at 100% load point, they basically have the identical efficiency or very close to the identical efficiency. How come then when we're looking at this point, so again, I have a 100% load point on the 2-chiller at 100%. How come right over in this mid 50% point where I'm turning on a new machine, so that machine ramped up to 100%, and I'm just about to turn on the second machine, how come those numbers are different? It's 100% load, but the one with the VFD is less kW per ton. And it really comes back to the point where we're looking at lift and load reduction, right? So as far as lift, at that 50% building point, I have cold condenser water. Because I have cold condenser water, I reduce lift. The VFD on a centrifugal chiller is a lift reducing device. Okay, so therefore I'm able to have better kW per ton with the chiller plant at 100% load with cold tower water. That's why the blue variable speed drive blue line that represents 2 400-ton variable speed centrifugals is better. Okay, I think most of the folks on the phone in the industry recognize that VFDs make an awful lot of sense. That's why, from a carrier standpoint, I believe we're at around 90% of every centrifugal that we sell has a variable speed drive on it. Now we're going to talk a little bit about our 23XRV screw chiller. Okay, so the variable speed 23XRV screw chiller, it says here 300 to 550 tons. Actually, I apologize. We just recently have a new compressor that came into the lineup on this machine, and it's from 250 to 550 tons. What we did here with it, because VFDs are so prevalent, we put a VFD standard on it. We optimized around 134A because that's the refrigerant that almost every major player has in the marketplace, and it has no phase-out date in the United States. ASME pressure vessel, and we have the next generation tri-rotor screw compressor. So that's what we're designing, and all our chiller plant energy analysis pieces are going to be designed and optimized around the 23XRV screw chiller. This is a picture of the screw chiller. It is extremely robust. It's basically, I got shorter rotors. It's not like a twin rotors machine. I have shorter rotors. It has no slide valve. If you talk to folks who don't like screw compressors, they're going to tell you a couple reasons why. They're going to say, A, I don't like the maintenance on the machine because of slide valves. Well, we eliminated the slide valve. And the other thing they're going to say is, I don't like the high-pitched scream of a screw compressor. This is actually quieter than a centrifugal. Okay, so this is a very quiet machine, and it's a very robust machine. And if you look at that compressor, it is built like a tank. Okay, Carrier started producing this chiller back in 2004. Okay, they have approximately around 1,000 of these machines in the marketplace. We have a compressor that's sitting in our parts location, still waiting to be used for the first failure we experience on one of these machines. Again, these machines have been all over the world in all different conditions, taken care of, not taken care of, and there has never been a compressor failure. This is unprecedented in the industry itself. So if you look at the tri-rotor and why we can do this, okay, it's got a balanced rotor design, so forces on the compressor cancel axially and radially. Okay, because I have very low bearing loads, I'm able to use less oil. The machine will operate with as much oil that's in the palm of my hand, and I have extremely long bearing life. The bearing life on this machine, the lowest bearing life on this machine is 500,000 hours, which means one thing. We never intend for you to do a compressor overhaul on the life of this machine. There's no stop majors for doing compressor overhauls on this chiller, which is significant because if you talk about a centrifugal chiller, basically you have manufacturers looking for a 10-year or a 20-year overhaul that could cost as much as 40,000 and 50,000 hours. Even if you're looking at the magnetic bearing piece machine, you have to change out capacitors and other items, which could add up to approximately $5,000 every time you have to change out a capacitor, which could be as much as once every 3 to 5 years. Again, we're looking at the machine. It's different than typical screws because I can actually operate it with cold condenser water. Okay, it's got its own independent oil distribution system, so I can now basically pump oil to the bearings, and I can operate this machine down to 55-degree tower water. And I mentioned before, it has 500,000 hour bearing life. No 10-year or 20-year overhaul cost required to an owner. One of the key pieces here, and I'm going to go back to the slide again here, and that is, you look at this, the 23XRV, it's different than a centrifugal. And the reason why it's different is because it's a positive displacement machine. It doesn't obey the fan laws that are required on a centrifugal chiller. So I could basically achieve 75% speed reduction on the chiller, whereas a centrifugal can only achieve 35% speed reduction. And a 23XRV is a part load and part lift device. You heard me talk earlier about how centrifugals are part lift chillers. This 23XRV screw chiller is a part load and a part lift. That's why it's more efficient at every operating point with part load and part lift than any chiller in the industry. So if we look here at this little chart, we have a day where we have clouds over the sun. All right, I'm able to get colder, wet bulb temperatures, and therefore my machine is able to do some speed reduction. Well, on the top, on the 23XRV, I'm able to get significant speed reduction. On a centrifugal, I'm able to get 65% speed reduction. Now my load doesn't change when the sun comes out. dramatically. It will change eventually, but it doesn't change dramatically. But what happens on a centrifugal machine? The sun comes out. It's now not overcast. My tower water, my wet bulb temperature shoots up. Because the centrifugal is a part lift device, it then has to track the weather. So therefore, my speed of my VFD ramps up. Okay, and the 23XRV is still able to just maintain the load in the space. It is not a part lift device. It is a part load and part lift device on a machine. So that's why the 23XRV is so much more efficient than a centrifugal. And we sell centrifugals too. Our 19XRV is a very efficient machine. I'm just showing you basically the differences between our tri-rotor 23XRV and all centrifugals. Again, simple, reliable, 3 moving parts, 57-year individual L10 bearing life, no stop majors. I have no purge, no shaft seal, no valve, no slide valve maintainment. Okay. One of the key things, and we're going to go into the performance here, but this is the real piece that really makes people's eyes light up when we talk about this machine. We had a chiller that was operating, and this was one of the first beta site chillers after it's been operating for a year in Fayetteville, Arkansas. And this machine was running at around 300 tons when it experienced a tower fan failure. Okay. Now, again, Carrier kind of went back and they said they heard back from the operator that the chiller operated through a tower fan failure. Okay, this was pretty significant. So we combed through all the data and we came up with the following chart. And we show here that the condenser water temperature went from 72 degrees and shot all the way up to 105 degrees, and it ran with 105 entering condenser water temperature for 12 hours. Now, it didn't run at 300 tons, but then again, no chiller would run with 105-degree condenser water temperature out in the marketplace. That's not a positive displacement machine. But the Carrier 23XRV did, and it delivered 150 tons for 12 hours while that tower fan was repaired. Once the tower fan repaired, it started and went up. So this building was not without cooling at all. This is a significant piece. Okay, this is very significant when we talk about chillers and overall basically reliability of a system itself. Shows you how fast we have 80% rate of change of flow on the 23XRV. Typical centrifugals are anywhere from 30%. Machines without electronic expansion valves. Machines with an electronic expansion valve, that means machines with magnetic bearing compressors, have a 10% rate of change of flow on the machine. If you've had one out in the marketplace and you've noticed they've been sensitive to flow, that's because they're only capable of attaining about 10% rate of change of flow, whereas the Carrier 23XRV is able to handle 80% rate of change in flow. We're able to cut the flow in half on a machine. If you look at a parallel chiller plant, when I basically go from turning from one machine to two machine, my flow splits in half. Okay, so once that flow is split in half, can my machine handle it and stay on the line? The wide operating range, basically the operating range is everywhere in that block and the extreme zone. So I could run with cold condenser water, I can do inverted starts, I could run at low load, high tower. This machine, there's no other chiller in the marketplace that has the operating envelope that this machine does. So we kind of wanted to talk a little bit about the 23XRV and show you how I implemented it into a chiller plant design. Now I'm going to go into a specific problem and show you the energy results here. So we had a customer request for 3 267-ton chillers in parallel to handle 700 tons of load. Okay, why did they want three 267-ton machine? Because at any point, the owner said, I need to have 525 tons of critical load required for the building itself. Okay, so I needed 525 tons of critical load. So I oversized machines to have 3 267 tons to handle a 700-ton load. Because really, three 233-ton machines would actually handle a 700-ton load. I have a primary secondary pumping system. I have a 44-degree leaving water temperature and a 70-degree return, 85 entering 3 GPM per ton, and the end user's request was energy efficiency is an absolute priority. Hold on a second. So let's look at the schematic on this. Again, 100% load point is 700 tons. So I have 3 machines in parallel delivering 233 tons apiece. Okay, and I'm just going to basically what this engineer was looking at was running 3 turbo core machines because in his mind, based on the marketing, he thought this was the most efficient chiller in the marketplace. Okay, so I have 3 machines running 400 GPM delivered to each. Okay, primary, secondary system, and if one machine goes down, I could deliver my 525 ton minimum load. So what we did is we said, let's look at an alternative to this. Okay, let's look at 2 525 ton machines. And then what we're going to look at here is we're going to look at something called running redundancy. Okay, so I have 2 525 ton machines, and I'm going to do series counterflow. At any time, if something happens to one machine, we have a 525 ton critical load that's met. And we're able to do that while the machines are running, which means there's less downtime in overcoming that thermal bullet in the system of the chill water system. Okay, so I changed it from everything in blue is what we changed. I went from a primary secondary to a variable primary pumping system. I have 44 degree leaving, again, 60 degree, everything the same. And again, energy efficiency was a priority. So what is series counterflow? If we look at series counterflow, basically I have 60 degree entering return water, entering chiller 1, chiller 2, and leaving 44 degree leaving chiller 1. Sorry. 85 degree entering chiller 1, 95 degrees leaving chiller 2. So my coldest entering condenser water hits my coldest leaving chilled water. Okay. Again, upstream chiller cools 60 to 52, downstream 52 to 44, and evaporator chiller 2 to chiller 1, condenser chiller 1 to chiller 2. And we'll go through some of these a little later here. Okay. Here is my diagram of my 2 525 ton machines and a variable primary load. If any time, now they're going to run at 350 tons. 350 tons each. Now, the benefit to the 23XRV is that I can oversize it and not take a penalty on efficiency. Okay? However, you cannot oversize a centrifugal and not take a penalty on efficiency. Because in order for me to size a centrifugal, I have to size the wheel to handle the mass flow to get the tonnage. If I'm oversizing my wheel, that means when I'm not operating at that optimal point, I'm running less efficient. So the 23XRV, I could actually run it at reduced load at as good or better efficiencies than the design. So I could run it at 525 tons and have good load at good kW per ton, and I could also run it at 350 tons and have it at good kW per ton. So let's look at the results here. So I have 3 parallel 267 ton machines, and CS is constant speed. That would be basically 0.65 full load, 0.566 part load. Condenser water 240 GPM. And again, I have 3 267 tons. That one is basically the one they were looking at, the most efficient operating, which is 0.629 full load, 0.403 part load. Again, 1200 GPM, 2400 GPM. And then I have 2 series counterflow centrifugals, constant speed, 2 525 ton series counterflow centrifugals, variable speed, and then I have the 2 525 ton series counterflow variable speed screws, full load, part load. Okay, when you're looking at from an engineer and an end user, when you hear basically the terms of 0.629 full load and 0.403 part load for a chiller plant, that is, you basically be very excited about those efficiencies. Now you're looking at full loads of 0.496, part loads of 0.316. Now you may be asking why my condenser water flow and my evaporator flow are the same. Now I'm doing a variable primary system. I'm doing a variable primary system on the variable speed screw options. On the constant speed 267 ton machines, I'm doing 1200 GPM because I have a primary secondary system. I'm always pumping that GPM. On the condenser side, The reason why I can't reduce my condenser water GPM is because my lift, when I sized that original 267 ton machine, is based on 2,400 GPM of flow. When I reduce the flow, I increase my lift, which may cause the chiller to go to surge, which the variable speed screw can't do. But I'm able to reduce the condenser water flow and reduce the evaporator flow on the two 525-ton series counterflow machines. So I'm 22% better than what a lot of engineers would call the best 3 chillers in the marketplace. Okay, and I'm 44% better than the ASHRAE minimums, okay, in the marketplace. So 22% and then 21% better than full load. So what are the tailored solutions? So we have, so with this option, I gave them fewer chillers, fewer pumps, same redundancy, better efficiency, better reliability, and less floor space. And there's no 10-year overhauls, and there's none of that, okay, associated with this machine. So let's look at the series counterflow and how we do this. And again, it's all about lift reduction. We talked about this earlier. It's all about lift reduction. And we'll go into this a little more in detail here. So if I look at a parallel chiller plant, I have 2 parallel machines, and they always have to deliver 44 degree of water out of each machine. And I always have 85 entering and 95 leaving on a design day on those parallel machines, okay? On a series counterflow, on the downstream of chiller, I still have 44 degree leaving, but I have 92 degree saturated condensing temperature or 90 degree leaving. So I actually save 5 degrees of lift versus a parallel chiller plant with this application. Okay, when I reduce lift, I save energy and I save kW on the system itself. Now let's look at the upstream machine. The upstream machine is even more significant. So now, instead of delivering 44 degree water out of that machine, I'm delivering 52. So I have a 50 degree saturated suction temperature. My condensing temperatures are the same, but I'm changing it from 55 degrees of lift to 47 degrees of lift. Again, I'm reducing lift on the machine. I'm lowering lift. I'm lowering kW on the machine itself. So therefore, when I do that, I save energy and I have a better operating chiller plant. Now, this is really cool. So now we start talking about increasing the delta T, because I think from what we're looking at, increasing the delta T on a coil. Now, you can't just say I want a chiller plant with a high delta T. I have to have coils and air handlers that can deliver the high delta T, because one of the biggest issues on a chiller plant is low delta T syndrome. So in this case, if I can actually get and maintain a constant delta, increase my delta T, my series counterflow chiller plant actually gets more efficient as the upstream temperature goes up. So as I increase the delta T on the chiller plant, my upstream machine, its temperature goes, its upstream delta T goes up. So therefore, I'm actually saving energy by going to a higher delta T. Now let's look at going to variable primary flow. So now I have a constant flow pumping system or a variable primary flow system. Now when I go variable primary flow, I'm able to maintain my delta T. If we look at a constant flow system, so I have a variable primary flow on top, I'm maintaining a delta T throughout the load, okay? Whereas on a constant flow system, again, my delta T drops as the load drops. As the load drops, I would actually pay a penalty in efficiency if I was doing a series counterflow. But if I do series counterflow variable primary, I actually increase my efficiency by going to variable primary flow because I reduce the lift on the upstream machine. Okay, that's the key piece. Again, it's all about reducing the lift in it. So now we're basically looking at saying, okay, I'm going to save pumping energy because I'm increasing my delta T. I'm going to variable primary flow. I'm doing all the good things, and at the same time, it's making our chiller plant more efficient. So therefore, that's why series counterflow makes a lot of sense. So let's look at it here. So the frontier of what we're looking at here. So I'm going to go from left to right as I'm looking at my computer screen right now. Constant speed, CS, centrifugal, parallel flow, parallel chillers, 4454. ASHRAE says I'm at 0.549, 0.576. So 0.576 full load, 0.549 part load. I now take those machines and now make them variable speed centrifugals in red. I go to 0.576 full load to 0.399 part load. That was a chiller plant that everybody was saying, I like that chiller plant, that is the best in the industry. Now let's look at variable speed screws, the 23XRV variable tri-rotor screw, parallel, 44 leaving, 54 entering. Again, this machine doesn't have to be piped in series. It can be piped in parallel and still be more efficient than every chiller in the marketplace also. We're just showing you how it's that much better. 0.56 full load, 0.358 part load, okay? And then variable speed screw, series counterflow, flow, 4454, 0.517 full load, 0.334 part load. Variable speed screw, series counterflow, variable primary flow, 4454, 0.517, 0.324 part load. And then the last one, variable speed screw, series counterflow in peach, series counterflow, variable primary flow, increased delta T, 4460, 0.498 full load, 0.302 part load. And the reason why I could show you those pieces here is because in the test, we ran this in an actual test at 800 tons, and you can see there at the bottom, the design was 0.51. The actual came out to 0.498 in testing when we ran this thing through a chiller test at our factory, at our AHRI factory in Charlotte, North Carolina. And the part load design was 0.313. Actual kW per ton on that machine, 0.302. Okay. Now you say, how can we actually do better than this, right? Well, we came out with something called a 23XRV part load optimized chiller. I went over through this in the last presentation, but what we did is Carrier basically optimized around the part load, the place where the machine operates the majority of the time. Not the 100% load point, but the 75 and below points in the chiller operation. Okay, and we are able to break the 0.30 kW per ton barrier. No chiller in the industry has ever done that, and we achieved a 0.299 IPLV on that chiller. So now let's look at where we're at now. So now with the part with the part load optimized, we are able to achieve 0.269 part load efficiency with the part load optimized machine. Again, the full load went up, okay, 0.520. But how often do we operate a building at design day when the building's fully occupied? It almost never happens, right? So we're 11% better than the previous best-in-class 23XRV running at a 0.302. So we're running at a 0.269 from a chiller plant standpoint at 800 tons. No one else can touch this in the industry. So I want to show you guys, I want to show everybody on the call right now the differences between series and parallel. And I think the best way of showing this is by comparing the exact same chiller by going from parallel flow through the machines to series flow. Now when I go from parallel to series, so I have a two-pass typically in a parallel flow plant. When I go to series, I have a single pass. Okay, and I'm going to single pass because I don't want to take the pressure drop penalty hit. So let's look at a 23XRV 4040 chiller. The 4040 dictates the amount of copper that's in those cooler and condenser shells, each at 400 tons. So in this case, I am running 400 tons at 0.566 full load and 0.346 part load on this chiller. 44, 56, 85, 3 GPM per ton on the condenser. I now take this and I go from series I go to a Series 23XRV 4040. The cost didn't change on the system. Okay, it's the same cost of whether I go to a 2-pass chiller or a single-pass chiller. You're talking about the same exact cost for chillers. Okay, so now my downstream machine is now 0.544 full load, 0.334 part load. And again, I'm going to go back to the last slide. Again, remember 0.566 and 0.346. That's a parallel. The machine didn't change. All I did was go from parallel to series and change it to 2-pass to a single pass, and I reduced the lift. My upstream machine went to 0.526, and my part load was at 0.286. Okay, full load efficiency 0.535 series, 0.566 parallel. Part load 0.31 series, 0.346 parallel. 12% improvement. My total pressure drop on the cooler on the series is 15.4. My total pressure drop on the condenser in series is 21.2 versus the previous, which was 19.3 and 13. So I take a tiny penalty drop on the efficiency on the pressure drop, but I gain tremendous amounts of efficiency on the chiller. Now let's do the same exact thing. Let's look at our part load optimized machine, and I'm going to skim through this fairly quick because I know. Well, here, I'm going to skim through this very quick. So I got 0.625 full load, 0.324 part load, and I changed that, and now I'm at 0.309 full load on the downstream machine, and I'm 0.252. And you look here at the bottom column on the top sink. So I have my downstream chiller 4450 and my upstream machine 5056, and I'm basically taking the machine and I'm going from 0.324, which is industry leading, to 0.309 NPLV and 0.252, and I'm saving approximately around 13.3% efficiency on my part load value. So with the 23XRV rule of thumb, I could take the same exact machine and I could go from, and I can basically take this and I can go from parallel to series, and without adding a single bit of cost to the chillers, I can gain 10 to 15% efficiency by going from parallel to series on a chiller plant. So a couple of series counterflow selection criteria. I think we mentioned this before. Full load very rarely happens. Make sure when you're sizing a tower, you are able to provide low load with high tower, especially new buildings where you have a new building and I have a brand new chiller plant and tenants are not always all moved in yet. It needs to operate at reduced load with high tower, high lift. The 23XRV is able to do that easily. Just make sure when you're dealing with whoever you're dealing with, they are able to do that also. Added benefits to series counterflow. I call this the Band-Aid, right? The biggest problem of a chiller plant is low delta T syndrome, okay? How do you solve low delta T syndrome? Well, you have to try to somehow handle your coils and your air handlers and fix that part of the building in order to increase the delta T of the system. However, if we look at a chiller plant, the bad part about low delta T syndrome is sometimes if I'm running one machine and I need more flow on a parallel chiller plant, how do I get more flow? You get more flow by turning on a second chiller. So I may be running at, say, 50% load on that first chiller, and I need more flow for my plant because I have low delta T syndrome. So what happens? I now have to turn on the second chiller, and now I'm running two machines at 25% load to handle the flow. That's probably the worst operating point of a centrifugal chiller, and therefore then I'm also over pumping, and all those bad things that go with low delta T syndrome itself. With the 23XRV in series counterflow, I have two machines in series. I'm able to run one machine at whatever, say 50% load, and actually run more flow through it if I needed to have more flow. Again, it's a Band-Aid. It doesn't fix the problem. It's a Band-Aid if you have low delta T syndrome. It prevents me from turning on a second chiller. Lead projects, ComEd dollars, significant. We did a project just recently, and I believe it's 4 machines, series counterflow, and could achieve well over $150,000 in ComEd rebate dollars. So that's you could call me about specifics, but series counterflow, we can do a custom rebate on it, and it will get the most dollars of any chiller plant out there from a ComEd dollar standpoint that we've seen. Okay, so when we select chillers to handle variable primary flow, we need to maintain a minimum of 1.5 feet per second or greater at all times in the cooler. So that's basically one of the criteria on minimum flows on a series counterflow variable primary flow system, which is very low flows on there. On the 23XRV, I have a 70% minimum rate of change. I told you 80 before. That is correct. This is an older slide. They've updated to 80% rate of change of flow on the 23XRV. Minimum rate of change of flow on a centrifugal. Majority of centrifugals without EXVs is 30% rate of change of flow. Here's a photo of a 23XRV RM where I basically have a marine water box on the sides, and they're connected to one another. So there's a photo of a chiller plant operating in series counterflow. From a control standpoint, how do we want to control it? Again, I have chiller 1 programmed as the lead chiller. Chiller 2 is programmed as the lag chiller. Chiller 1 would load up to approximately around 80% compressor speed. And unlike the centrifugal, speed equals load. Okay, so 80% speed. At 80% speed, chiller 1 will command chiller 2 to turn on. They will both be operating off of a common leaving water sensor. And then chiller 1 will then make sure that we're optimized. And then when we turn off, we're going to be at 35% compressor speed. Then chiller 1 will command chiller 2 to turn off. Okay, so that's basically the controls of the machine itself. What I do recommend when we do a series counterflow plant is we have some bypasses for chill water. So if for some reason one machine has to be serviced, you could still run flow through the other machine. And here's a series counterflow drawing here just for your reference. If you have a project and you want some specific drawings on your machine, just contact either your salesman or you can contact myself directly. So I want to do a sample problem. Hospital project, 400-ton chiller replacement. Okay, 44-degree leaving water, 56-degree entering water, 85-degree entering condenser water, 3 GPM per ton. Existing two 400-ton machines, R11 single-speed chillers. Owner wants to replace one 400-ton machine right now. Year-round cooling and heating requirements. Okay, so they actually have year-round cooling requirements is what they have. And they plan to replace the 400-ton machine. And actually, this is, again, I apologize, I did this presentation in 2000, beginning of 2012, in the end of 2012. So either way. Option 1, let's look at a 400-ton Carrier 19XR centrifugal constant speed machine. Okay, 4456, I'm running it at 0.574 full load, 0.528 part load, the chiller itself. Option 2, a centrifugal with the variable speed drive, 0.574 full load, 0.373 part load. Option 3 would be a 23XRV. And I want to kind of, one of the things that's great about this product is you can replace, you could change out heads in the field. Okay, so let's say today this is a 2-pass chiller that I put in. Maybe when I turn out that second machine later on in 2013, I order that as a single pass, and I buy single pass nozzles for the machine, a 23XRV, and I do a series counterflow. In this case, I didn't do that analysis, but that is an option that you can do when you're looking at 23XRVs and changeouts, because a lot of times they don't have in the budget for changing out both machines. They only have one. Well, you buy the first one, you put it in parallel, knowing that in another year I could change it over to series by changing the heads on the machine itself. So again, here's an option 3, 400-ton 23XRV tri-rotor screw, 0.595 full load, 0.319 part load. Again, it went from look at the part load data, 0.528 on constant speed, 0.373 centrifugal variable speed, 0.319 23 XRV tri-rotor in parallel with the existing system. Let's do a little analysis and let's look at what happens to the system itself. So now I have my old R11 system, which was costing approximately around my old existing R11 plant, which was operating and costing about $76,000 a year to operate. I now change that one chiller to a 19XR constant speed going right to left. It cost $67,000 to operate. I have a 23XRV, which cost $51,000 to operate, and I have a 19XRV, which cost $57,000 a year to operate. So I'm saving approximately $25,000 a year by changing out a chiller that has to be changed out, right? So it's got to be changed out. Oops, hold on. So it has to be changed out, and when we look at here at the next slide, the 23XRV is going to be obviously the lowest life cycle cost chiller. And let's take a look at ComEd dollars. So ComEd will pay for the VFD on the dollar. So if we look at a 23XRV, and all these data is based on ARI conditions above, I'm getting about $32,000 a year for the 23XRV. In the Carrier 19XRV, I'm saving about $24,000 a year. So again, the price adder to go to a VFD on the centrifugal is about $20,000. ComEd basically will pay for that VFD retrofit with the incentive dollars by doing that. So now 23XRV, again, I'm saving $32,000 on ComEd right up front, and I'm saving $25,000 in operating cost per year. How do I get better than that, than operating my old R11 machines? Well, we can do better, and this is a lead into my next presentation that I do. That'll do. I think it's next week. Actually, is when I'm doing the next presentation, and that is we can do better. And the key is that I said this chiller operates year round. What we can do is we could do option 4, which is our one Carrier 400-ton Carrier 30XW heat reclaim chiller, dual compressor machine, can deliver up to 140 degrees of water, same conditions on the evaporator and condenser, and is it really more efficient than the most efficient 23XRV chiller in the industry? And the answer is, if I do a real quick snapshot example of what a chiller plant can do in this case and what the savings would be, if I'm operating at 1 kW per ton with a little bit of demand charge at $1 a therm, now those conditions are old, but if I operate that plant 4,000 of simultaneous heating and cooling hours, which is which is realistic when we talk about a chiller plant that operates year round, I'm delivering 120 degree water to the space, and I'm assuming 60% load, and I'm basically unloading an 80% boiler plant, an estimated savings of $122,000 a year. Again, when I take out the R11 machine, I'm saving $25,000 by going to the most efficient chiller in the industry. Look at heat reclaim. The heat reclaim is the gold in the building. Okay, if I could reduce the boiler plant load, that is the gold in the building. Okay, so that's where I finish off with this presentation. And if anybody has any questions, you could now send them over to me. So hold on a second. Let me start looking at the questions here. Okay. Okay, so one of the questions here was to maintain lower condenser water, you will need to run the condenser fans and pumps more. And has that energy been considered? And the answer is yes. Yes, you are taking a penalty by running and if you look at any of the analysis that I do, and I can show you that anytime I do this, you'll actually find that the tower energy on a series counterflow plant will be more significant than a parallel plant. However, the overall energy consumption of that chiller is better. So the overall efficiency is better on a series counterflow chiller plant. So yes, that is a great question, and that is taken into account. Okay. Any other questions here? Okay. Is there any incentive from NICOR with option 4? Um, my my answer to that is contact me directly, and we believe if you get myself and Ryan Hoger involved, there is some incentive dollars for some heat reclaim machines. So yes, get us involved in that, and we can discuss that. I'll hold on for just a couple more minutes. If anybody has any questions, type in. After that, I am going to sign off here. And if anybody has any specific questions, again, you could send me an email directly, mike.smid, S-M-I-D, at tecmungo.com. Or if you just want to call me on my cell phone, 847-630-7867. Okay? So actually, Jim, actually I said, has variable condenser flow been considered? Yes. That is a consideration what you could look at, and you have to, in your analysis, you have to determine, and we could look at that. There is a point when you do want to have a flow on the condenser at certain points. Yes, it it can make sense, especially if you have a lot of hours operating at colder condenser water temperatures, um, at extreme condenser water. I mean, be, below 50 degrees, because then I can actually slow down the flow if I want to make sure my machines stay online. But yes, you can look at doing variable flow through the condenser. I don't normally recommend it because as I reduce the flow, I increase the lift, especially at those the normal operating points. But yes, people have done the analysis, and there are certain points where it's going to make some sense to reduce the flow. Okay, I am going to sign off now. Again, thank you very much.